everybody. Welcome to the second slot of faculty presentations. Last week went quite well. We're going to start with Jeff Moore, and I think that as we did for the second half of last week, let's have each presenter advance to the first slide of the next talk so that there's no confusion. And without further ado, take it away.
So, I have to teach one session in the field, so I'm going to do this and leave. I'm sorry to everybody else, I'm not trying to be rude. Yeah, I'm Jeff. I've been faculty here since 2013. Before that, I was at UT Zurich. Before that, Berkeley. Before that, University of Arizona, and I'm from Tucson, Arizona. A lot of what I've done here in the last 12 years involves using ambient vibration measurements to study the structural dynamics of natural geological features, mainly rock arches, have been the main subjects. To do that, we use seismometers, place them on a rock arch. That's Paul and Riley, some ex-PhD students here. And leave them there 1 hour to 24 hours. Analyze the data then for spectral content, frequency information, identify resonance frequencies. Analyze the data for polarization information and other like mechanical and dynamic attributes like the entropy. We then have a sort of workflow going with photogrammetry, numerical modeling, results in these wildly exaggerated animations which show the different modes of vibration. So we can compare our field data to these numerical models and validate the field data and get a better idea on the model strain fields, frequencies, etc. We do all this for sort of three purposes. The first is for structural mechanical characterization. That's material properties and boundary conditions. The second purpose is for structural health monitoring. That's like searching for shifts in resonance properties over time to try to identify damage in these features. And the third is vibration risk assessments. And so we are asked from time to time by the Park Service, does this or that factor somehow adversely affect the structural integrity of these arches? And those factors are often things like earthquakes and wind, but also interestingly weird things like helicopters, road traffic, and so on. Over the years, extended the methodology to different subjects. This Tabernacle Hill Latitudes here, really cool site in central Utah. We did ambient vibration study in Matterhorn. Again, measured its resonance properties and a couple other Swiss mountains. We had a seismometer on the summit of Matterhorn for 3 months. It got flown there by helicopter, really weird stuff. The third photo is a large Faline rock slab located near the Moab Airport. It's kind of topping over. The crack's 500 meters long, sort of in and out of the picture. And then we used an array of seismometers to actually measure the vibrational mode shapes, and then an inversion procedure with numerical models to invert for crack depth along the crack. So this is boundary conditions characterization. And then we did a whole study on various sizes of rock towers. That one's funny, little one here, Moab. Another sort of central focus has been landslides. Ancient modern Zion here, that's my daughter, in front of Zion Lodge. And the big question you can ask is, why does Zion have a flat valley floor at all? Well, it has that because there was a giant landslide about 5,000 years ago. A lake followed that in Zion for about 800 years. The lake filled up with sediment, and we're still flushing out that sediment today. That's why they're having such deep disturbance. Spent a lot of time working with colleagues here in the department on the Bingham Canyon slides over in the pit. They were from 2013. Interesting, very, very large slides. Currently working in Alaska with USGS and Molly McCreary, looking at development of paraglacial landslides, especially kind of a long-term focus on in the last tens of thousands of years, how to develop rock damage through thermal mechanical processes. Currently working in central Colorado with Kate Evans there on controls and distributions on very, very large, deep-seating landslides. You can see one just over the GPS receiver there in the image. These are sort of ridge to valley floor scale giant creeping landslides. Into the future, sort of stumbled into this, but a lot of the same analysis techniques can be applied to ancient Native American masonry structures. This is Hovenwood Castle. It's an ancestral equivalent site in far southeastern Utah. More work there, kind of the Park Service, same kinds of questions, same kinds of techniques. couple recent studies. We had a seismometer and summit at Devil's Tower for 24 hours working on that. Just finished a study on saguaro cacti, same kind of thing. Now it's a biomechanical characterization. And that's the spout project for next year, looking at vibration of sea stacks and how flexural strains can contribute to erosion in the underlying areas. That's all for me. I have to run.
Hello everybody, my name is Frank Keeling. I'm a professor in geophysics. I haven't get to there yet. So I joined University of in 2013. I teach a lot of different kind of geophysics courses like seismology, seismic imaging, magnetic earth, that's good. And over the years, I would say I'm not just a faculty, I'm also learning. And one evidence of that is now I could teach, I'm qualified to teach review of earth science. And I remember when I first joined, there's a faculty meeting, like one faculty said, oh, we should make sure everybody in our department know how to recognize calcite. I know, and I'm qualified to teach for review, so that's good. Okay, so I want to give you guys a little background on how I get here. So I'm originally from Taiwan. When I grew up, in Taiwan, we don't really focus on like what you're interested in, we focus on what you're good at. You're good at math and physics. And when I go to college, my brothers say, oh, if you don't know what you want to do, just do physics and you can do anything afterwards. So that's what I did. I got my physics degree, and then the problem is after you did that, I still have no idea what I want to do. So I actually get into a kind of geochemistry lab. So I have experience working with DNA and protein. And then I got lost again, and my father just said, if you don't know what to do, just come to US or go to US and get a degree in like whatever. So I applied, and I screw up with my GRE, and so I ended up needing a backdoor channel to get to a school. Like I went to Drexel University, and I studied protein folding. So essentially using physics tool to kind of stretch a protein and try to see how it reacts. It didn't work out very well. One thing I learned about bio-related research is that it's very hard to reproduce. So sometimes it works, sometimes it don't, and I have no idea what I did wrong. So I tell myself I need to do something more robust. So I get into astrophysics, try to do simulation, study how n-body will rotate with each other, and how black holes will interact. And the only problem is that there's no data to compare. You have a lot of prediction, you have no data to compare with. So I get sick of that. I convert to do atomic physics. I get into a lab and work for one semester. I remember I built a circuit board, and the professor just look at it and just throw it and just me to get out of that. So I realized I'm not good at my hand, right? I'm just thinking coding and programming. And luckily, I was able to find what ended up working for me, which is geophysics. Okay, so that's how I get into geophysics. Exactly what I do subsurface imaging. We go to different areas, find interesting geologic feature, and try to understand what's the relationship between subsurface structure to the surface. For example, we do a lot of study in Yellowstone, try to understand magmatic structure beneath Yellowstone. So that helps us to understand the potential status of the volcano, what's the potential hazard there. In Salt Lake City, we have also used seismic imaging technique, try to study the valley here. So I can tell you in the valley where the sediment is thicker, and if you want to buy a house, you probably want to avoid those areas. So basically you can see that in this part here, between the East Bench Fault and the West Valley Fault, we have a thicker sediment, and that's probably where I suggest you to avoid. So that's like if you have a big earthquake, that can potentially amplify the seismic energy. And other than that, we also study Yellowstone, like the conduit of the geyser. We look at the seismic signal and try to study how the conduit extends further deep. And we can see that it goes down to about 150 meters. And also this geyser, which is Steamboat Geyser, have a companion structure next to it. It is called system pool, and we try to study the interaction. And I don't know if I want to do it again, but it was like a fun experience. So with that, I thank you for your attention.
I'm in 40th grade, and this is my 11th year at the University of Utah. I'm a paleomagnetist or paleomagician by training, and I'll tell you what we can do here in a few seconds. But primarily what my group does is use mineral and paleomagnetism in a variety of Earth system science applications. So we study iron because it is very abundant. It's the fourth most abundant element in the crust. Most abundant element on the planet by mass. And iron has very unique physical properties that give rise to various forms of permanent and induced magnetization. So it's able to track a variety of different Earth processes, from the physical Earth to environmental science to even atmospheric and planetary processes. So it makes it really fun. Also makes it sometimes difficult to concentrate. So I will say I sometimes have, or usually have, science ADD. As you'll see here in a minute with what our group is working on. But our primary research themes can be broken down into a few topics, albeit very large topics. My bread and butter remains tectonics, studying orogenic systems and crustal processes. And I put in here fluid-rock interactions, because our group, particularly over the last decade, 15 years, has done a lot of work on tracing iron, what happens to iron-bearing minerals in a variety of fluid rock interactions, whether it's in carbonates, in serpentinites, in lavas, etc. And what that means, the implications for those fluid rock interactions in terms of understanding the fidelity of the magnetic record that we then use to ask other questions about the Earth and planets. Another kind of characteristic of paleomagnetism is the ability to tell time. So we use magnetostratigraphy, and so we use geochronology to study more specific questions about like how quickly do certain things happen with the geodynamo, the thing that gives us our magnetic field. What is the tempo of eruptions in Yellowstone or in the Black Rock Desert of Utah, for example? It also allows us to put dates and give rates on biological processes and climate processes, and also correlate stratigraphic sections across ocean basins and continents. It's very useful that way. And a lot of work in environmental science, particularly air quality, and probably something a lot of you haven't heard about, I'm guessing, is biogeomagnetism, so microbes and higher organisms that also make magnets. We make magnets, we don't use them, but we do make magnets. And studying these applications, both in terms of Earth and the environment. So, kind of give you an idea of what we're working on. My lab group, so Sandy's working on air quality, using magnetic methods to understand a variety of air quality related questions, both here in Salt Lake and in the LA Basin, that we can then hopefully export to other areas. Tori, another PhD student, now working on magnetic records of strain histories and iron mobility in deep sea rocks. She did her master's here that she completed recently on fault rock magnetism, which is a really cool study we're trying to get out. Co-supervised Justin with Carrie, and that's a big tectonics project. How do ocean basins disappear? And I have a bunch of undergraduate researchers working with me. Margaret is using those microbes that make magnets, the fossil remains of those microbes, to understand environmental change across our descent into the ice house. Kaya is working on also this closure of the Mongol-Okhotsk Ocean in Central Asia, but a very specific focus question related to that project. Shelby is working on understanding what's carrying the magnetic signal in these low temperature explosive volcanic eruptions, so that we can ask some interesting questions about how those even happen. And Ramon is working on characterizing the mineral magnetism of a geothermal prospect in southeast Utah. Sorry, southwest Utah. How do we do this? We do it with a variety of field work. I feel like the older I get, the less field work I do, which is kind of sad, because I used to do a lot of it. But we work both in the oceans, and rest in peace, Jody's resolution. This vessel doesn't exist anymore. But this is a space shuttle of Earth science, I would say. And a few of you in the room have sailed on this as well and used materials collected by this. But we still do a lot of traditional field work map and compass and looking at rocks. And then a lot of lab work, both electron microscopy and a variety of magnetic methods. Courses I teach, this is my normal ensemble of courses, and this is not the normal year, so I'm not teaching any of these courses. Instead, I'm currently teaching Magnetic Earth after a many year hiatus, and I'll be taking over field methods in the fall. So yeah, Asaku was like, use these talks to say like, what would people come to you with questions for? And so we move continents and we close ocean basins, we tell time, and we'll tell you about the iron that's in your rocks, sediment, air, meteorites, whatever. If it's got iron, we'll tell you something about it if we can, and we can do a whole lot more with that.
Hi, I'm Tori Sterling, and I'm trying to figure out how to retire. So I guess my career can be described as just there are isotopes in everything. So if you have anything at all, it will somehow be involved with isotopes. And then at the bottom there is a favorite quote of mine, even the wrong road leads somewhere. So you might think you're going somewhere in some scientific direction, and perhaps it'll lead to something else that may be more interesting. I started out a long time ago doing just simple geological mapping, dating, and tuff correlation. And that's me sitting out in the field when I was a graduate student in an area about 300 miles from the closest electricity, so my microscope was using the sun for illumination. I got involved early in isotope studies, so 50 years ago, published a paper with Garnis Curtis redating one of the most important fossils at the time, a fossil known as 1470, which we ended up starting a big controversy by dating this to be 800,000 years younger than it had previously been dated. Our plus or minus on that was about 200,000 years. And just last year we published a paper on dating the same ash that now we can date to plus or minus 1,000 years. So we've now been able to push from multiple orbital cycles into well within orbital cycles. Other things that I've been involved in is in using carbonates to date, or to do paleoenvironments. I got into that about 40 years ago. That paper there at the top, Sterling 84. Now for Fanchi, Tyler Hughes is at the bottom of this pit, which is actually down in the Boulder Mountain area. And this is actually a giant landslide that took place about 200,000 years ago, which we dated using cosmogenic carbon-14 in the Noble Gas Lab upstairs with Kip Solomon. So we're interested in using the carbonates as paleoenvironmental indicators, and we can, with uranium series dating, we can go back to almost 500,000 years and get climate information. So Fanchi, this is the place to go for carbonates. With great big black boulders with white bottom. The white bottom are carbonates. Okay. This is actually the 1470 skull, but I've been involved with paleontologists for a long time. And one of the things that I try to work on is testing paleontological ideas about things like morphology and paleontological diets. Just last week we published a paper on some behavioral drive versus morphologic changes in primates and other animals, showing that often the diet changes, as shown by stable isotopes, leads the morphological changes by 1 million or 2 million years. So that's one area that we're interested in. My work in paleontology has led me into working with animal physiology. Here we're trying to collect camel breath. They weren't that interested in us doing that, but so we're actually looking at the methane CO2 ratios in breath of many animals, trying to understand the fractionation factors that defines why we use different fractionation factors for different taxa in reconstructing animal diets, and also recently been involved in looking at amino acids in animals, trying to figure out what is the turnover time of amino acids for using to reconstruct actually modern diets, which I've gotten into studies of wildlife conservation for the last 25 years, working with Save the Elephants and Save the Rhinos and a bunch of other things. George Whittemire there in the bottom, kneeling down. There's a guy kneeling down, actually taking molds of elephant teeth that we use to compare the diets. I'm reconstructing diet histories using tail hairs of animals. This slide here is Kevin Uno working on forensics of wildlife products. So we're working on where wildlife products come from using both genetics and strontium isotopes, using the strontium isotope lab upstairs with Diego to determine where illegal ivory is coming from. We've done a whole variety of things on forensics, including fake malaria pills, which just about has to be one of the saddest things that I've encountered in my career. So, in closing, all those
Very thin slide, much more isotopes. So my name is Chad Ostrander. I'm an assistant professor in the department. I've been here since 2023. Before arriving here in 2023, I was a postdoc at Woods Hole Oceanographic Institution. It's the East Coast and cooler version of Scripps. And before that, I was a PhD student at Arizona State University. I've lived in Southern California. I've also was born and raised in Southern Oregon. I'm an isotope geochemist, as you might be able to tell by my first dirty stuff. I am the PI of the platypus. This is a lab name we're trying on. If you like it, you might not ever see this again. And the Paleo Laboratory Plus. We're non-traditional isotope geochemists, so a lot of the work that Turi and others have pioneered over the past many decades has focused on the lower end of the periodic table. Those isotope fractionations are very large, they're very easy to measure. Now instrumentation has evolved to the point where we can measure really small isotope ratio differences on much higher mass elements deeper on the periodic table. So I spent a lot of time working with Diego in the ICP-MS lab on the multi-molecular ICP-MS up there. We have a new one arriving sometime, hopefully by October. They'll be able to push us into the future more for non-traditional isotopes. I really like working with elements like vanadium. I work with iron quite a bit. I work with molybdenum isotopes. I work with uranium isotopes. And I've worked most with, recently, thallium isotopes is one of my favorite. All of these isotope systems I've been able to leverage because they're all redox sensitive. So when you're moving electrons around, you can change the size of an atom. That also changes its bonding environment, among other things. That drives large isotope fractionation effects. So all those elements that I just mentioned are all redox sensitive. So I'm very interested in using those isotope systems to track modern redox sensitive processes, and even in more detail, what's happening with redox in Earth's past, way, way, way back when. So me and my group, I have 3 PhD students now, as of this fall, we study modern, non-traditional isotope cycles. We like to go to places like aquatic water bodies. We've done some work in the Baltic Sea. We try to go to environments that the chemistry is quite weird. It's chemistry that is really rare today, but was perhaps really abundant on ancient Earth. The Baltic Sea is a place where there's only oxygen in the surface waters, and at depth, it's anoxic, there's no oxygen. It's really rich in sulfide, it smells like rotten eggs. You bring that water out. We do a lot of work in places like Minnesota, where you have 10,000 lakes, even more. And you can find any chemistry you want there, and so we have some of those lakes have the chemistry that we like. We apply this knowledge to the ancient rock record. When we can, we try to target cores, because those materials have been below Earth's surface and are less likely to have been messed with by modern processes. And our ultimate goal is to reconstruct Earth's past environments. When I say past environments, if you go to AGU and you see someone use the word paleo, it can mean a heck of a lot of things. But for me, for my group, we do really deep time is the word we like to use. I'm interested in what's happening on Earth billions of years ago to hundreds of millions ago, hundreds of millions of years ago.
think I'm the youngest one to talk so far. I'm the first one to use AI. Ask ChatGPT what the history of oxygen on Earth is. It'll tell you that there was no oxygen at our surface at some time, and then you had this something happened, the Great Oxidation Event, and then it's modern Earth. So some of this is right. There was no oxygen way early on. We had this event called the Great Oxidation Event, but it's quite confusing what happens after that. And there's about 2.5 billion years since the Great Oxidation Event to today. It's not like we just flipped a light switch and we got there. So yeah, my group is really interested in these two curves that have been generated for many decades now by myself and colleagues. This is Earth's history 4 billion years ago to today. This is the history of atmospheric oxygen, the partial pressure of oxygen in the atmosphere relative to today. So this is a present atmospheric level of 1, so that's 100% of the oxygen we have in the atmosphere today. In the bottom is someone's attempt to show what's happening in the ocean at the same time. You have this big kick of oxygen, this great oxidation event. Once you get oxygen in the atmosphere, you also start to get oxygen in the surface ocean. They share a boundary. You get some diffusion across the two. What's happening much later on is much more confusing. Here, this is the difference between some and none. It's pretty easy to track. This is the difference between some and some more. That's really hard to track. So in terms of research projects in my group, one of my students, I'm just going to go in terms of geologic time, Andrew Siciliano, is working on the Great Oxidation Event. So he's really interested in what we've been finding out the past decade or so is that the Great Oxidation Event itself wasn't a very binary event. It's not like someone flipped a light switch and then oxygen was forever at our surface. This is a really complex event that probably unfolded over multiple hundreds of millions of years, where you have rises and falls of oxygen. That's really exciting to track. The rock record really stinks around here, so Andrew and I have to work really hard to find good rocks to try to test hypotheses. Moving forward in time to the Tonian period, Michelle Norman is a new student in the group who is really interested in what's happening before the Neoproterozoic snowball Earths. So in the Neoproterozoic, the Cryogenian, which is named for its large ice episodes, the Earth kind of dives into these snowball Earth glaciation events. I might call them slush ball Earth. There's a lot of really cool things that happen after that. But right before it, we have some really neat changes in eukaryotic diversity. We have these things called base-shaped microfossils that appeared for the first time in the rock record. It seems like in really cold environments, perhaps, if you ask some people, maybe even on land. So Michelle is really interested in what environments were these organisms evolving in, what were they living in. Are these the first eukaryotic land organisms? And that would extend the record of land life back by 400 million years, which is really monumental. Last but not least, moving forward in time to the Cambrian period, 510 million years ago or so. Carrie Meza is another student in the group who is interested in the Cambrian radiation of animals. I've been working a lot, mostly on these two big transitions in Earth's history, the initial rise of oxygen during the GOE, and then this mess of what's happening here. What's happening when animals appear in the fossil record? Is this accompanied by some massive change in ocean oxygenation? Depends on who you ask. If you ask me, I don't think it's as dramatic as people think. We've done a lot of work when animals first appear in the rock record in the Ediacaran period before the Cambrian. There's no strong evidence with the tools we use, at least, for widespread deep marine ocean oxygenation. So Carrie's pushing that record forward to see what's happening during the Cambrian radiation. The Cambrian is special. You don't have to be studying geology too long to hear about the Cambrian explosion. Those organisms do look like they have high oxygen requirements. Can we find evidence that oxygen? And so that's me in a nutshell in my group. And yeah, just to kind of summarize, I'm an isotope geochemist again. I work with the heavy elements, non-traditional isotopes. And I look forward to seeing you all around the building over the coming year to years.
Timer. Hi, I'm Kate Ritterbush. I've started going by Kate since my sabbatical because if I say Kathleen, I will get Kathy, Catherine, like 50 different things. But if I say Kate, it's only one syllable and people will actually use it. So I really like that. I'm passing out toys, people who've taken my classes, which include paleobiology and now the thrilling marine biology through time, know that I'm really into things we can do with our hands. I won't say that I'm different from Fan Shi in being good at doing things with my hands. I like doing things with my hands, and then when I'm bad at them, I have that like love of accidental science that you do when you're wrong. I have had the great benefit of being here for 10 years now, which is very exciting. I'm a paleoecologist. I like studying marine ecosystems from the time of dinosaurs and earlier. So compared to Chad's timeline, that's a little bit on the end from like 1/3 of a billion years ago to 500 million years ago. And I am between grad students right now. So I'm working with a lot of fabulous undergraduates. I've run a National Science Foundation funded research experience for undergraduates for not this summer that just closed, but the 2 previous ones. And it was spectacular and amazing, and it kept me on my toes, and I learned so much, and it was totally exhausting. So I'm on the fence about whether I'm going to continue that. But the previous time that I did it was all students from SLIC, which was awesome, because then 2 of those students are here now, which is great. I haven't transferred in. And my work spans field work. Like a lot of people, I find I'm not doing it as much now that it is nearly impossible to get permits, and I also have a small child who notices if I'm gone. So I'm planning to do more of that in the near future when she doesn't care if I'm gone because she's got the soccer or what have you. But we did take students out for the REU. This is near the Triassic-Jurassic system boundary out in the desert in Nevada. But a lot of what I love to work on are ammonites, and ammonites are extinct squid-like animals. I have a stuffy for, it could be terrible things. I have a stuffy and a fun, digital gizmo to help you kind of get a vibe for what they are. If this is going to start up here. I'll hand that one to Randy. I think I just passed that around. Hopefully it'll work. It just crashed. That's my life. Yeah, so I work on a lot of stuff, but I wanted today, since I only have a couple minutes, to just show you everything breaking would be super fun. I wanted to show you just 2 projects we're working on. So my previous student, Nick Hebden, is on his 2nd postdoc now. He's doing a postdoc it's in Waco, at Baylor. But he's doing it remotely, so he gets to live here and hang out in the lab that he built when he was a student a decade ago. So, and this is us being very scientific with Josh Lively, who is the curator of the museum in Price. And with Josh, what we're working on is trying to say, can we reconstruct the bodies of ancient sea monsters like mosasaurs, ichthyosaurs, plesiosaurs, all those good things? And if that ever works, they're in there. Is it working?
I just had to hand it to Turi.
Oh, that's why. Yeah, it's in the isotopes. He's good with them.
Good with my hands.
Yeah! Josh did his PhD on mosasaur anatomy and what have you, so he knows the bones. I got really good during my sabbatical at making 3D models, like all the animals that are swimming around in here. I made those. I'm good at it. I use video game stuff that I work with colleagues on. So I can make the 3D models reconstructed from the skeletons, and then Nick is doing the fluid dynamics of how these things would actually swim. The going concern with these things is always, it's basically a big torpedo. You can ignore the fins. Don't ignore the fins. They actually do a lot of the heavy lifting, and I mean that in more ways than one. So this is stuff that we're doing that I've always kind of wanted to do just because sea monsters are great. And I don't even work on things with bones, but it's really fun to be kind of support team on that one because I'm just making the models. Now, the thing I'm obsessed with, I love ammonites, and I passed out, if you have 3D models, I passed out, Bennett, when you hold up the big stuffy. Okay, that's what an ammonite is, an extinct animal that had a seashell. But this is an animal alive today that is an open water octopus that never lands and never can lay eggs on a rock like regular octopus do. So only the females generate a hard structure that looks on the outside for all the world like an ammonite shell. But it isn't the same kind of shell as a regular seashell, and it isn't have chambers on the inside. And they can get pretty big. So what we are asking is not just how do these things move through the water, because we can see them in the wild, and not just what's the drag and flow limitations around these shells, but are there features to do with, this is looking at dynamic pressure. As this animal jets, I took this model from Los Angeles. I spent a lot of my sabbatical 3D scanning things and making surface models. I smoothed off all the ribbing while keeping the geometry and put it in a simulation of flow. And the dynamic pressure is on the outside of the shell, sort of pressing where it would collapse in, and then the eggs would fall out if it didn't have a way to resist that. The ridges channel that dynamic pressure across that surface, leaving areas of a lower order of magnitude pressure in between. So I know what calcite is, but these are like nanoflorets of high magnesium calcite. And that's not the same as snails. So I'm in a world of trying to learn more about the physics and how the biomineralized structures have this level of dynamism that isn't just, oh, it's an object, it's a torpedo, you can spitball it. What is it really doing? So yeah, if you are a grad student and you're not mine, come find me, and maybe I'll be on your committee, especially if it's deep time. That'd be fun. Okay, thanks guys.
Hi everyone, I'm Kip Solomon. One of the things I study is groundwater, which is what I decided to tell you about today. That's, some of you know, is the largest unfrozen reservoir of fresh water on Earth. It allows us to live in the desert, and it feeds us, feeds the world. But there's a lot of parts of the world where we're now overexploiting that resource. One of the reasons for that is that while the storage volumes are really large, the fluxes into and out of these are not. So much of my research is really centered around a really simple concept, that is that the mean residence time of fluids in a reservoir are related to how much is there and the fluxes that come in and out. This, we have all kinds of geologic tools to measure. It's the fluxes that are hard, so we're trying to make measurements of residence times. So this is genius Will Mace up in the lab making magic here. We make measurements of all kinds of things. Oh, this is making me keep on time. We make these measurements all around the world in some unusual places. This is the Greenland ice sheet where actually if you go 10 to 20 meters below the surface of the ice in certain places, there's liquid water there that stays there all year long, and we've studied this just like an aquifer. Closer to home, we've studied groundwater systems here in the Moab Spanish Valley. Here's Nora Nilsson. By the way, if you stop in Moab for a tea, you got about a 99% chance of drinking water that came from the Moab Springs up by the golf course up here. And by the way, that's water that's about 3,000 years old. Here's Kendall Fitzgerald, who studied some of these age dating tools in Salt Lake Valley aquifer here, trying to understand its vulnerability to contamination and so on. We also make a lot of these measurements where groundwater discharges. So this is Eric Humphreys using some of our seepage meters to quantify groundwater as it seeps into springs here, or seeps into streams. Remarkably, if you go into, and this is in the Sandhills in Nebraska, if you just go into this river and you poke a pipe down into the bottom and you, just a few centimeters, tens of centimeters, and you pull some water out, it's 10 to hundreds of years old, and it has, you know, remarkably consistent patterns as you move. The oldest water's out in the middle. If you go downstream where the river's bigger because it's got more groundwater that's coming in, and you do the same thing, you pull water out, now it's actually thousands of years old. So if you actually find yourself in Nebraska, you know, grab the family, grab a case of your favorite beverage in one of these stock watering tanks, and you can sort of immerse yourself in the past by floating, they call it tanking, down the middle of the river here, because you're literally floating on water that fell as precipitation 7,000 to 8,000 years ago. More recently here, a number of faculty members here, graduate students, both in the department and then collaborators at the Utah Geological Survey and USGS. We've been studying groundwater in its relationship to the Great Salt Lake. The center panel here is a figure from Sam Carter's thesis where, you know, we've observed that we got young groundwater near the mountain front that gets older and older, but then all of a sudden as we hit the playa, we get really old water. In fact, it's older than we can actually date with carbon-14. We don't even know how old it is right now. And yet, our geophysics friends and some of our direct measurements tell us that this is all fresh water underneath there. So there's some interesting things and implications there. And then finally, a couple of just ongoing projects. Tyler Yoklevich is using some of these techniques up in Cache Valley. He's looking at groundwater ages. You know, they get, you know, start in the mountain or mountain front, go from 6, 20, 30, 60 years. we're going to try to use those to then constrain numerical models for sort of the sustainability of groundwater use in Cache Valley. And then Colton Williamson is trying to use radon so that we can locate where some groundwater is discharging directly into the Great Salt Lake, and then hopefully quantify that. So I think that's all for me.
So I'm Michael Thorne, and I'm going to tell you a little bit about what I do today. And most of what I have been working on in all of my career has really been focused here in the very deepest part of the mantle in what we call the D-double primary. And really, a lot of that has been focused on something that are just really thin patches sitting right on top of the core mantle boundary that are called ultra-low velocity zones. So, ultra-low velocity zones have to be some of the most extreme features we see anywhere inside the planet. These have S-wave velocity reductions by as much as 50%, but they're just thin, 20, 30 kilometer sort of thick regions sitting right on top of the core mantle boundary. The way we approach looking at these is through something that we call waveform modeling. What this is basically we propagate seismic waves through models of these features. This gives us predictions of what the seismic wave field should look like, which can then we can use to compare to real seismograms and say this is where these things are located, how big they are, and what these features actually are. So the question is, why do we care? Why do we care about these little things sitting on top of the core mantle boundary, some 3,000 kilometers beneath us? So what I want to tell you about is why we care, what the picture we have sort of developed over the last 10 years is as to what these things actually are and why they matter. So ULVZs, they may have been around for a long time. There could be many different mechanisms by which these things get formed, and some of these could be very old things that maybe sort of developed through interactions between the outer core and the lower mantle, sort of core mantle reaction products that could have been left over from the early magma ocean. There's even some speculation that could be left over from ancient moon-forming impact. Right? But what we've been showing over the last several years is that we actually think they're actively getting generated in subducting slabs. This is because subducting slabs are capped on one side by mid-ocean ridge basalt. Mid-ocean ridge basalt has the lowest melting temperature of anything we know that goes down into the lower mantle. As this gets down into the lowermost mantle, this can potentially partially melt, actively generating new ultra-low velocity zones. So this is kind of what this looks like in information. The blue on the top here is mid-ocean ridge basalt. As the slabs go down, they buckle and fold. They fold over. Some of this mid-ocean ridge basalt can come into contact with the core mantle boundary. At this point, it is able to melt, forming an ultra-low velocity zone. What we've shown in about 6 papers or so in the last, starting in 2019, is that where we see subduction, subducting slabs where it hits the core mantle boundary, these areas are ringed in ultra-low velocity zones. So this updates this picture that, okay, we may have some old ULVZs from old types of processes that they've got formed way back at the beginning of the Earth, but we're actively getting new ULVZs forming right at the margins. Okay, but that's not the end of the picture, right? Because what happens is, as this material, as the subduction slabs start to continue to go down to the core mantle boundary, what is happening is this is pushing mantle material all around the inside of the Earth. And what happens is this ULVZ material, which is shown here in orange, also gets pushed around. And it gets pushed around until it accumulates into piles. It accumulates into somewhat stable piles, and these piles tend to then concentrate underneath upwellings in the mantle. So now, in this picture here, is we have the old material, long ago, got pushed aside, got shoved aside, and it got jammed up into places maybe on the edges of large low velocity provinces, but it all tends to collect underneath whole mantle plumes that give rise to hotspots. And new ULVZs are getting generated at the edges of the subducting slab. As those are getting generated, they're getting pushed to replenish this. So what we've also shown in a series of papers is that wherever we see hotspot volcanoes, those hotspot volcanoes are rooted in ultra-low velocity zones. We've seen this beneath Hawaii, beneath Samoa, beneath Caroline, beneath Galapagos. We've shown this in almost all of the biggest hotspot volcanoes in the world. So to summarize this, what we see is hotspot volcanoes are rooted in ultra-low velocity zones. Ultra-low velocity zones are the rooting spot of whole mantle plumes that come all the way up from a core mantle boundary to give rise to this volcanism. Right? These are replenished at subduction zones. These ultra-low velocity zones, we've shown they have really, really weird properties. They're probably enriched with iron. This iron gives them a very, different sort of thermal conductivity than what's in the ambient mantle. Mineral physicists can't agree on what that thermal conductivity is at this moment, but it's probably what it's doing is keeping these spots hotter. What that has to be doing then is fixing where these hot spots are located, and this probably explains why hotspot volcanoes have been rooted in the same spot for hundreds of millions of years. All right. So besides that, we've been doing all kinds of nonsense up in the mountains. Unlike everybody else in here, I've never done field work until like the last couple of years. Now I'm out every single weekend. So this is work I did with Yvonne and about half of last year's incoming graduate students. This is looking at Nogus, and this was electrical resistivity tomography. It took like 8 of us to carry 300 pounds of gear up here to do this. You get these beautiful images where you can see here's a couple of meters of the rocky debris on the surface, underlain by massive glacial ice. Right? With Bronson, he actually collected 232 gravity measurements over the top of the glacier, and we have over this last year done sort of 3D Bayesian inversion of this. These are cross sections that are going this way through the glacier, and this is real. What we see here is as much as 55 meters thick of ice at the deepest point, and this is real. This has been sort of confirmed now by a lot of the work that we're doing this fall with Yvonne involving magnetometry, transient EM, and we've also been doing ground penetrating radar. Besides that, I spent much of the last year doing electrical resist, just a ton of electrical resistivity and transient EM work around the Great Salt Lake. With Mason, this is Mason. This is Surrey at one of our beach days. The umbrella is not for Mason, it's for the instrument. Thank you.
Hi, y'all. This is a special hydrologic advisory report for the Great Salt Lake Basin. It's being brought to you by Low Earth Orbit Van Dam, myself. The urgent alert for northern Utah. The water balance of the Great Salt Lake Basin is reaching critical lows, as evidenced by water levels in the Great Salt Lake. Water levels in the lake have dropped by 15 meters since about the 1990s. These historic lows expose vast stretches of lake bed that are laden with arsenic, mercury, and other toxic metals that become airborne. Expect more frequent dust storms, reducing visibility, and endangering respiratory health in the future. Sensitive groups will include children, the elderly, and those with asthma. Estimated inflows to the lake contain significant uncertainty because groundwater and stream flow are difficult to characterize at the appropriate scale. Further, data on diversions are incomplete, delayed, or they're inconsistent across irrigation districts and water users. Low Earth orbiting satellites, however, tracking soil moisture, groundwater storage, and mountain snowpack report alarming changes. Groundwater storage decline. Long-term satellite measurements show the groundwater reserves beneath the basin are in retreat. Pumping and reduced recharge are drawing down aquifers that buffer supplies in dry years. This loss is invisible on the surface, but it reduces base flow to rivers and weakens the steady inflows that sustain the Great Salt Lake through the summer. Here we're showing the satellite gravity observations of water storage in the Jordan River basin, and we're comparing it to base flow that reporter Paul Brooks gave to me so that I can compare you. And if you look at the long-term trends, well, it's pretty sad because groundwater is going down. But one of the good news is that it is tracking with the base flow. So when we previously thought that this satellite the footprint of this satellite was too big to look at anything like this, what we're seeing is that we're actually getting information back, at the basin scale. Our affiliates at SMAP are also reporting a soil moisture emergency. Across the Wasatch and Uinta foothills, soils are running drier than normal. The past July, KSL reported that Utah is now the only state in the country to be 100% under drought. It's the first time the entire state has been fully under drought conditions since December of 2022. Groundwater stores, the first line of defense against drought, are shrinking. This means that recharge for streams, less infiltration to aquifers, and more rapid drying of farmlands. Here's a picture of what's happening to soil moisture in all of the 3 major river basins that feed the Great Salt Lake. What's interesting is that this satellite image is showing us that it can look at 3 separate basins, and the differences, it's observing differences between the different basins. And when we compare the soil moisture to stream flow in this case, we see that the response of stream flow to the soil moisture in these basins is very different. So we haven't had time to really go into this and understand what's happening in between basins and amongst the whole system, but it's not looking very good at all. Our affiliates at MODIS have issued a snowpack warning. Winter snows, the lifeblood of the Great Salt Lake Basin, are increasingly unreliable. Snowpack is peaking earlier, melting faster, and leaving less water for late season runoff. This report shows how MODIS snow extent varies from year to year and from basin to basin, indicating that this low Earth orbiting satellite can capture differences again at the basin scales. So what you see here in blue is the percentage of snow area, and in red is the same stream flow information going into the Great Salt Lake from these different basins. The satellite can see differences amongst the basins, and we're seeing the response of the stream flow very different from basin to basin. Again, we need to look into this a little bit more, but without sustained snowmelt, the Bear, Weber, and Jordan rivers will deliver less water downstream, starving the lake at the very time it needs replenishment. The long-term outlook, soil moisture, groundwater, and snowpack paints a pretty grim picture. Dry soil, shrinking aquifers, and diminished snowpack form a triple threat to the basin's water supply. Without coordinated conservation and adaptive management, the Great Salt Lake will continue to recede, leaving dust storms, ecosystem collapse, and economic loss in its wake. Remote sensing can offer more coherent and consistent data across all of these water basins, and also across the Great Basin itself. And as a warning, it's probably not a good idea to invest in agriculture, municipal golf clubs, or brine shrimping fields.
Okay, my name's Sarah Works. I'm starting my 2nd year here as an assistant professor, and I'm a hydrologist or a critical zone scientist, which is this concept of all of the spheres of the Earth interacting to store and transmit sediments, solutes, nutrients, water, the things that drive life. And so I'm particularly interested in how humans and climate are impacting the way that all of these spheres interact together. And I spend a lot of time studying streams because they're sort of mirrors to watershed processes. So they integrate upstream change, they integrate spatial and temporal variability. And this picture is of a stream, a mountain stream in Colorado, and I think it does a nice job capturing these themes because you can see changes in water quality through time as a function of mixing flow paths. So I took this in the late summer a couple years ago. Flows are low, and the stream is coated with iron oxides because the pH is low. So groundwater that's flowing through these fractured mineralized rocks is upwelling into the stream. pH is about 2 here, so it's quite low. But during high flow, when snowmelt mixes in with the stream, the water level rises, and then as pH goes up, because you have a change in flow path, you actually have aluminum oxides precipitating out. And so here, the mineralized rocks, the geosphere interacts with the atmosphere, driving snow. There's some amount of evapotranspiration losses due to this vegetation, all to drive the amount of water and the quality of water in this stream. And so, like I said, I'm interested in how humans and climate are impacting the processes that drive these reactions, the storage, the things that shape water quality and quantity. And so lately I've been thinking a lot about long-term analyses of water quality throughout the United States, and also site-scale studies, so different ways that humans can sort of fundamentally alter these processes. One thing is thinking about how warming throughout the United States has caused sort of ubiquitous increases in silica all throughout different regions, different climates, different geologies. And one hypothesis is warming of the shallow subsurface is impacting solubility, exacerbating weathering, and we're actually starting to see more silica in streams everywhere. So this temperature warming is actually changing water-rock interactions. In mountainous regions, like places in Colorado, I've observed increases in calcium, sulfate, decreases in pH, and one hypothesis is decreasing rain and snow cause falling water tables, which change air-water interfaces, causing more redox reactions, oxidation of pyrite, things that are degrading water quality. So exploring ways that humans are impacting water-rock interaction processes. I've also thinking a lot about water availability through a stream drawing lens. So when we conceptualize streams, we think of them as having water in them, but headwater streams, these small streams that feed downstream water resources, tend to dry. And that drying can be really spatiotemporally variable. So this is 4 months, and then distance and flow is blue, dry is yellow, and there's lots of heterogeneity here. And so using all sorts of tools, geochemical modeling, age tracers, GIS analysis, hydrometric analyses, I've demonstrated that the geosphere, so the properties of the subsurface, depth to bedrock, porosity, permeability, fracture density, impact where streams are going to dry. And so moving forward, I'm really interested in exploring how these changes in weathering and changes in water availability are going to impact downstream water resources. And so working on some new statistical and machine learning analyses to try and think about how this upstream heterogeneity propagates downstream. So as hydrologists, critical zone scientists, we can sort of infinitely characterize heterogeneity, but getting at how important that heterogeneity is, particularly as we continue to change things, is really important. And I'll add one more data point to this inverse relationship between age and number of days in the field. I spent lots of time out there this summer with some wonderful students, so setting up new watersheds. Red Butte just behind campus, then Albion Basin and Little Cottonwood Canyon. Was out there with geochemists and geophysicists, some undergrads, Ellis and Cameron and England, who might be in here, and then Ryan, a new graduate student working with me, trying to get at some of these questions about propagating upstream heterogeneity downstream.
I'm Randy Irmis, I'm a paleontologist, and I'll try to go quick since we're over time. So I have 2 roles here at the university. I also, in addition to being a professor here in the department, I'm also curator of paleontology at the museum, the Natural History Museum of Utah. So if you haven't been up there, come up and visit. But that's also why you may not see me around as much. I teach most recently one of the field capstone courses, but I've also taught Evolving Earth and World of Dinosaurs in the past. So all my research centers around how we can test hypotheses about how ecosystems in deep time respond to external forcing like paleoenvironment, climate, things like that. And to do that, I collaborate with a bunch of different people using a lot of different fields of geoscience to answer these questions, particularly data from paleontology, but also geochemistry and geochronology, stratigraphy and sedimentology. My heart really is in the Triassic period, but I've got ongoing projects from the late Paleozoic all the way down to the Holocene because I can't say no to new interesting things. And just to highlight a few recent things that are ongoing. So I've been working with Gabe Bowen and colleagues to reconstruct latitudinal temperature gradients for the Mesozoic, taking these diverse proxy data and then comparing them with global climate model data to see if we can get a better handle on what these climate gradients were like in deep time. We have a long-term project in the late Cretaceous of Grand Staircase Escalante National Monument and recently published on the big desert lizard. This is a new species of fossil lizard that's related to modern Gila monsters and tells us some interesting things about the ecological structure of late Cretaceous ecosystems. in southern Utah at the time. We have an ongoing National Science Foundation funded project looking at the Carboniferous Permian transition in southern Utah in the Paradox Basin. This is a time when the Earth was in an icehouse state called the Late Paleozoic Ice Age. And we see a transition from more aquatic ecosystems to more terrestrial ecosystems, and we're wondering how this might relate to changes in ice sheets. So that involves paleontology, but also geochronology, stratigraphy, cyclostratigraphy. So here this is a filtered 125,000 year cycle of magnetic susceptibility data. So we're actually able to look at Milankovitch timescales back nearly 300 million years ago with these data from cores. And then also working in caves with Holocene fossil bone assemblages led us to ask how are these ecosystems responding to changes in paleoenvironments? So we've been collaborating with colleagues from Vanderbilt University and studying stalagmite records for Banshee's edification. This is calcite right here. So Samuel Bowman is in the room, helped out with the collection of this stalagmite most recently that we hope has a detailed paleoenvironmental history from the last 4,000 years for the Wasatch Front. But we also do things like collect modern drip water, put out glass plates to collect modern calcite, and also have drip loggers to understand the context in which these are forming. Thanks so much.
Okay, I think I'm last. Is this an audio thing for everyone? Okay. Anyway, yeah, Carrie Johnson. Everybody's saying how long they've been here. I've been here since 2002. I interviewed right before the Winter Olympics shut down the university, and I plan to retire before the next Winter Olympics. University. A quick note about teaching before I launch into research. Thank you for my SEDSTRAT folks that came to support today. I'm teaching SEDSTRAT this fall. And in the spring, I'm hoping to teach a field trip-based course that I've modestly called The Tectonic Evolution of the North American Cordillera. And in my vision, this is a field trip-based course that would cover the severe foreland across the Basin Range, across the Sierra Nevada, Great Valley sequence, all the way out to the San Andreas Fault. So we'll catch it all. I'm going to send an email out around to grad students and undergrads, 5, 6, and 7,000 level cross-listed, to try to get some of the logistics together for that. So watch out for it. I work in sedimentary basin analysis, and like everyone else that's talked today, I do lots of different things, some of which is listed here. I decided to use a trick that I use in my classes sometimes to frame literature searches, which is to use the old wedding adage, something old, something new, something borrowed, and something blue to describe what you do. Something old is me. My research in Mongolia, this was my PhD work. The pictures in the upper right corner include me as a grad student with my PhD advisor and my grad school buddy Laura Webb on a petrified tree trunk in southern Mongolia. And I'm just so fortunate to still be going there on the regular. Laura and I still work together, and they've added some new characters with Justin and Pete Lippard and many others. This is kind of my second geologic home, maybe even my first in some ways, but we get into all kinds of good trouble there, mostly in the realm of really big scale tectonic questions and continental questions. Something old and something new, at least new to me, is geothermal resources, and specifically geothermal from sedimentary basins. And that's different from kind of the Forage Project and hot dry rocks and what we kind of talk about a lot in this department. But anyway, I'm fortunate to be learning from and alongside Alex Bretman on this work. He knows much more than I do about geothermal, but we're trying to kind of put together a story for a part of southwest Utah near the Forge site that takes advantage of these thick sedimentary basin deposits. Something borrowed is our work in carbon utilization and storage. And I characterize this as borrowed because it's not exactly petroleum geology in reverse, but there are some similarities. But we borrow a lot of the same tools and techniques that we use for outcrop characterization to subcrop, sub-outcrop prediction, or subsurface prediction, excuse me. In this application, and Rohana Bowers is working on a CCS project in the Navajo with some help from postdoc Liz Mon on this. And then lastly, something blue for me is something out of the blue, which is relatively recent work on reservoir sedimentation in Lake Powell, the sometimes blue waters of Lake Powell. I'm going to be giving a full-length DLS on this on October 30th, so please come back by. But new student Emma Chris and I are delving into the terrifying world of geophysics here and trying to kind of expand our perspectives to include the sub-lake floor of Powell. And then finally, I know people kind of put some personal details. I'm obsessed with a couple of things beyond rocks. This is what I look like when I'm playing league tennis. Very competitive. So US Open's going on right now. Other things that I like to do, I like flying, and I like dogs, and I like flying dogs. I followed in Gabe Bowen's footsteps a few years ago to become a private pilot, love flying around, and because of the dogs, I fly rescue missions for dogs needing to get out of shelters and into foster and full-time homes, and I'm always looking for volunteer dog snugglers to keep them company in the back, so let me know if you'd love to go for a flight sometime.